Can everybody hear me?
Yes.
Good. Okay, so I guess thanks to the organizers for the invitation and the opportunity to speak about some stuff we've been doing over the last couple of years on polar active liquid crystals. So because this is in the liquid crystals, if you want, conference, I want to maybe do a sort of a little overview of the field of active matter, because I'm not going to assume that everybody knows what we mean when we talk about these active systems. And then I want to talk about maybe two problems that we've looked at. One problem looking at polar order emerging in thin films of active particles. And then I want to try to make an analogy with a totally different system, a system where you've got oscillations, and try to make the case that you can do very similar things to look at synchronization of oscillators as one does looking at these polar liquid crystals. And then I want to sort of, hopefully at the end, combine the two to talk about collections of synchronizable swimmers or self-propelled particles. So, active matter is, if you want, collections of some driven units which are consuming energy, and effectively the thing that makes them interesting from the point of view of, if you want, genericity, is the fact that the driving is happening as a bulk effect, not a surface effect, in the way that a lot of non-equilibrium systems that we're used to studying are. And there are many examples, you know, on many scales. So you could have large scale things like fish, and you could have small things like bacteria. And they're orientable, so you have possibility of having broken rotational symmetry. So I want to say something about the components. The components, these active particles. So they are these sort of driven elements, they're orientable, and we can sort of think about three types of active particles, if you want. One, particles which are not polar from their physics, but are driven. So you could imagine, for example, a sphere which is somehow driven. Or you could have systems which are active in the sense that there's the driving breaks the symmetry, but the particle is itself asymmetric. So you have an asymmetric particle with asymmetric driving. And then you could have particles which are symmetric. So you have driving, but the driving doesn't break the fore-aft symmetry. Okay, so if you want, these are the so-called shakers, which were mentioned in the last talk. Okay, so given these ingredients, you could imagine having some liquid crystalline phases. So one phase would be, let's say, these particles which have this polar symmetry. They could form a polar phase, or they could form a nematic phase. And of course, the particles which are apolar can only form nematic phases. There are lots of different examples on various scales. Here we have some melanocytes, and these are nematic. Here you have some vibrated rods, these are nematic. You have a cytoskeletal extract, so these are filaments of actin, like we had in the last talk, and the motomyosin, but just put on a plate. If you want a cell in vitro. And then you could also have catalytic colloids. So you've got particles which are polar in the sense of their driving. Okay, so we've got different types of particles with different types of order. And then the other thing is damping. So we can think of each of our active particles as having some drag from the environment, and it's moving in a fluid, so there's some viscosity of the fluid. And so there's an important interplay between viscosity and the drag, and essentially, you can't ignore hydrodynamics if you are on scales less than a ratio given by the square root of their ratio. So you could have systems where friction dominates, where you are in this regime, or where hydrodynamic flows are important. And I'm going to call those wet and dry. And again, looking at the examples we talked about before, if you had the collection of bacterial swimmers, then you would have the case where hydrodynamic flows were important. If they were dilute enough, their recent work suggests that maybe at very dense cases, hydrodynamic interactions might become less important. Or in this case of these filaments driven by these molecular motors, you on a slip, things will be friction dominated. Okay, so we have different types of particles, and if you want, different types of driving. So then let's talk a little about theoretical descriptions. So how would you describe these things? So well, you could start off with some agent-based model. So you have some bunch of these objects, and you have some rules for how they interact, and you just put it on a computer and study it. Or you can do, and of course, this started in the work of Vicek in the mid-90s, and has been continued by several authors. Or you could do sort of molecular dynamics, Brownian dynamics simulations where you had the objects, whatever they were, interacting with the fluid, and so essentially taking into account in some way the fluid background in which these things are moving. Or you could do kinetic models where you solve an equation for probability distribution of orientations and positions of the particles. And what I want to talk about today, though, are using sort of generalized hydrodynamic theories where you focus on some large-scale, long wavelength behavior, which are obtained by looking at the broken symmetries and the conserved quantities in the system. And again, we could do this whole thing wet and dry. So imagine the wet system, hydrodynamic importance. This was, as we hinted before, introduced by Sivan Ramaswamy and various others. And dry systems, of course, goes back to the early work of Toner and Tu in the 90s. Okay, so I am going to talk today about wet systems. So I'm going to talk about systems where hydrodynamic interactions are important. Okay, so I've got my object. It's driven, so there's no external forces. So if I do the integral of the stress tensor of the surface, I know that's 0. It's moving in a fluid. I am going to here consider the regime of low Reynolds number, so I can ignore the left-hand side of that equation, and I have a Stokes equation for the velocity field outside. Okay. So how would you describe such an object? Well, as we know, the total force must be 0. So if we try to represent it as a collection of point forces, which we are free to attempt to do, even if we are not successful in doing that, so we could imagine that we could do some multiple expansion of this object, and we would imagine that there would be multiples, various multiples. And of course, we know since the force is 0 that the monopole term must vanish. So we must start off at a dipole, and and if we think about a dipole, we can think of two types of dipoles. Either the force is pointing inwards or the force is pointing outwards. And people have now called those pullers and pushers. Of course, you could also have a quadrupole or higher order multipole. Okay, so if you want, your active particles are these multipoles. And in the rest of what I'm going to talk about today, I'm only going to consider dipole and quadrupole terms. I'm not going to consider anything else. Okay, so we understand how one of these particles behaves. So how do many of them behave? So many of the examples that I showed, though not all of them, were in thin films. So we could, if you want, we're going to study this problem in this thin film geometry. We could also study it in the bulk in 3 dimensions. So we have these force multipoles, and they're in a fluid, and we'd like to understand how they interact with one another. So we can use, if you want, the Green's function for the Stokes equation, and we can calculate the velocity field induced by one such object on the other. If we're in a thin film, then I could, for example, have a thin film suspended between a fluid which is less viscous, or I could have a thin film with a substrate. And if I had a thin film with a substrate, then I would imagine the substrate would damp out the motion, and I would go to this dry limit. If I have a thin film with fluid on either side, then I would still have to worry about hydrodynamic interactions. So we can solve the Green's functions for this problem, and we get some effective hydrodynamic interaction. So our point force of the origin generates a velocity field at position r, and this velocity field has this form, where it goes like 1 over r for short length scales, where the viscosity is dominated by things happening in plane, and it goes like log r. It goes like backwards. It goes like log r on short length scales when viscosity is in plane, and it goes like 1 over r on longer length scales. Okay, so how can we describe collected behavior? So the simplest, if you want, model you could construct would be to say that pairs of these particles, I can decompose my many-body system into a bunch of pairwise problems. So that's basically what we're going to do. So I essentially have one of my self-propelled particles. It's a force multipole. I can calculate the velocity field generated using the Green's function, and I can calculate how one will affect another. And so this object has 2 degrees of freedom. It has an orientation and a position, and they will have the position will be driven. The position changes because the thing is driven, and there will be some interactions which will be due to the other particles. The orientation to lowest order doesn't change, but because of interactions, the orientation can also change. Okay, so we're going to start off with, we have this simple model, and we're going to try to generate some hydrodynamic equation for the large-scale behavior. And the effect, the thing that we're going to do is ask what is the role of hydrodynamic interactions in these systems. Okay. So how do we do that? So we can write down some equation for a probability density, which satisfies the conservation law, which has a current, which has 3 terms. So first term there is coming from fluctuations. The first term is a self-driving term, which is coming from the fact that these objects are driven, and some interaction term, which comes from the fact that, which is from this hydrodynamic interaction with all the other particles. And as each of these objects can be described by prompt position and orientation. And this is just saying the same thing again. Okay, maybe just explicitly saying that since the things can move and rotate, we have translational and rotational currents, and the translational current has some fluctuations, which may be thermal or athermal. There's some driving and some interaction term. The rotational has fluctuations and just the interactions. And we have obtained these by looking at the hydrodynamic interactions. So now we want to coarse grain, so we want to go from what's happening on short scales, what's happening on long length scales. How do we do that? We do that by doing a moment expansion of the concentration, which essentially means we can project onto some set of degrees of freedom which are simpler. So we can think of conserved quantity, such as a density. We can think of a measure of polar order, which is just measuring locally at every position R what the mean orientation is. And you can define a second rank traceless tensor, which is measuring local nematic order. And of course, what we would like to understand is if the system is in an ordered state, then which was polar, then we would expect that this P would have some non-zero value. If it was in a nematic state, then we would expect Q to develop a non-zero value. So starting from our equation of motion for the densities, we can also project onto these density, polarization, and if you want nematic order. And let's look for at the beginning at bulk behavior. So we just ignore gradients. So I have now my polarization. So I've got rotational diffusion, which tends to destabilize any kind of order. And then I have some terms which are coming from the interactions. So they are you can see them from the interactions because they're quadratic in the fields. So they're basically two particle interactions. And the terms, these beta terms, are proportional to the force of the forced dipole. And essentially the sign is determined by the sign of the forced dipole. And so what you can see, now we can then ask what are the steady states of the system. So we can set the left-hand side of these equations to 0, and we just solve for the bulk behavior. And we find that, well, as a function of density, and depending on the sign of this, the system can develop polar order coming from the long-range hydrodynamic interactions. Yeah.
So to get polar order, you have to get the coefficient of P0, the beta 0, I guess, has to be positive.
Yeah.
Right? But then what stabilizes? Why doesn't it run away?
Okay, so, well, there are two ways. One, you could, I mean, actually the S naught here, when you, so you're going to solve this equation for S, and you can plug that back in, and that is a stabilization term. Okay. The other thing is, of course, you would expect that you have other things stabilizing, like steric interactions or other things, which would stop you from.
I was wondering whether this equation presumably involves some kind of truncation.
Yes, yes.
And if you went to higher order, would you also get stabilizing terms?
Well, if you went to higher order and did some kind of closure, like one I suggested here, then you would get stabilizing terms. That's generally how these stabilizing terms emerge. You go to higher order, and then you use some closure scheme to.
And they are actually stabilizing. They do have the correct
Yes, they have the correct sign. Yes.
Sorry, Tanny.
Yeah.
Reached this stage already, you have a closure scheme, right? Because you have some. What have you done? What have you
No, I've not done anything. I've just truncated. I haven't done closure. I've just stopped. I've just.
that's a kind of closure.
Yeah. Okay, so there's a hierarchy of tensors that we can get here, and we've just taken. I've said that the third, fourth, and fifth, and nth tensors are 0. Okay, and yeah, and so of course, since the sign is important, so what you find is that, because the sign is important, then actually there's very different behavior between pullers and pushers. So the pushers show the possibility of forming these ordered phases, whilst the pullers do not. You can also look at higher order things, the quadrupoles and such, and there, in fact, you find there's a nematic phase, but no puller phase. Okay, so, but this isn't good enough, because as we know, for example, from Mermin Wagner and various people, we have to check whether or not mean field theory is stable to fluctuations. So actually, we should look at fluctuations. So even if we see this interesting looking order, we should ask whether or not this thing is. I should say that if you do this with 3D hydrodynamics, you get nothing. All the terms cancel. So with 3D hydrodynamics, you do not get this. So this is really something to do with the fact that you're looking at the thing in this thin film.
So this is the thin film
with bulk fluid above and below. And so, yeah, so, it just, all the terms, in 3D, all the terms cancel. So it's really, I would say, it's very, I don't have a good physical reason for why that happens. But there must be some rule, but which I'm not clever enough to see. Okay, so we can then look at these bulk states, and as in three dimensions, as was hinted in the last talk, there are these instabilities to splay. Well, since we have pushers, we have an instability to bend. So this should be bent. Sorry.
So, Danny, why is the instability not there in 2D? Because let's say you have a bulk system with, I guess your system is the following. You have a two-dimensional layer of these active guys.
Yeah.
And you have bulk flanked by bulk fluid.
Yes.
Why can't the same instabilities take place in the plane of that 2D sheet?
Yes. So, I mean, they do. That's what. Okay.
I think you were saying they didn't accept it. No,
I'm saying is that we don't have this situation like you have in 3D. We have only this. So we have pushers, and they're unstable to bend. Okay, so we can do this both in the nematic phase and the puller phase, and as in the puller phase, you have a coupled mode of density and polarization, so you can get phases. You can get traveling waves of ordered directed material, and in the nematic phase, essentially the density doesn't vary. I would just say that if you look at the instabilities, they are soft compared to the instabilities that have been identified by, for example, Shriram in 3 dimensions, that they fall off with a lower value of K. Okay, so in some sense, the take-home picture is, yes, hydrodynamic interactions can give you local order, but this order is destroyed by the stresses which generate flows in the system. Okay. Okay, so if you want, so now I want to change tack a bit and talk about a slightly different system. And I want to make the case that actually we can understand these systems in a very similar way to the systems I've just described. So, well, ciliated organisms, we know, are around the things which have little hairs, if you want, and they can use these hairs to move. We also have cilia on various parts of our bodies. We have them in our lungs, the mucociliary tract, and so you have some mucus, which is what takes away all the dirt that our modern society generates, and and again, this mucus is sort of transported by these cilia moving. And so the question you can ask, in the same way that we asked about this emergence of long-range order, you can ask really, can you get transport of material by the cilia on scales which are much larger than their size? Which means, can you get the cilia to behave in some kind of collective way? And in a similar way to the last bit of the talk, I'm going to take a very complicated system. So this is what cilia looks like. So you've got a bunch of it's active in the sense that it's driven by molecular motors and filaments. They're organized in a rather complicated structure, and there's some binding and unbinding of the motors, which goes through some cycle, which leads to the motion of the cilia. So, but I'm now going to do the same thing we did for the particles. We're going to take a sort of multipole expansion, and so I'm going to approximate my cilia for now as a single point force, which is subject to a time-varying force. A point particle which is subject to a time-varying force, sorry. So we're in a viscous limit, so I know that the velocity is just the force divided by friction. And then my force is going to change with time. And I'm going to just write down the most general expansion that I can write out for the force. I'm going to say a little bit more about where these terms come from. So I've got a linear, so more or less these terms would correspond to sort of a linear and nonlinear spring, and actually this term is actually what can cause this thing to oscillate.
So that's supposed to be F, not F dot.
No, sorry?
This is the dot above that F there.
There's F dot, yes. This is F dot and this is X dot. So this is not.
It's not a spring.
It's not. Yes.
Yeah.
Okay.
So is this supposed to represent the force generated by the motors inside?
Yes. Okay. So the motors generate a time-dependent force, and we'll see. I have a toy model in the next slide, which will try to explain where these terms come from.
So is this like these models that people use for the fluctuations of cilia in cochlea?
In some sense, yes. Yes. So this is like a normal form of a system close to supercritical Hopf bifurcation. Okay, so what does this system look like? Well, how does it behave? Well, this is not, can you see? Yeah. Okay, it doesn't look very clear here. So you can start off, okay, so maybe let's have a look. Okay, so we can start off with any arbitrary initial condition. So recall this is our equation. Start off with any arbitrary initial condition, and eventually what's going to happen is we're going to just get on here and go and get on this limit cycle. So we have this limit cycle. So I've got two examples here. I started out here and I started there, and both very quickly went to the limit cycle, and I stayed on the limit cycle. Okay, so I just want to point out what. So you can get all this behavior with alpha being 0, but alpha being non-zero is interesting for the following reason, that it gives the system non-isochronous oscillations, which means that if you want the limit cycle, the frequency of the oscillation is amplitude dependent. So if you change the parameters so you have oscillations where when you change the parameters, you have bigger amplitude, but the frequency remains the same. Here, as you change the amplitude, the frequency changes, and vice versa. The other thing you should say about such oscillations is that the amplitude basically remains tightly constrained to the limit cycle, whilst the phase can vary a lot. Okay, so that's important to look at. So now let's think about how would you get such a...
Tanny,
yeah?
Now, you put the light back on.
Okay.
We're filming.
Okay, so again, how would you imagine, let's do a cartoon of how this would emerge. So now, so we can think of my whole array of filaments as just one filament. I've got I think of the body of the cilia as just a point force. I've got some motor, which is walking along the filament, which is coupled to the both to a rigid anchor and to the body by springs. I've got two springs. One spring, the spring which couples the particle to the body. If you want, I'm going to keep a nonlinear term, and I'm just going to keep a linear term for the motor spring. So I've got, again, force balance. The forces are some of these things. The motors have some binding and unbinding. So you can do a sort of simple model, meaningful model, and you can calculate what the effective, how the force changes with time, and you find out that you can get estimates for all these terms. And I should just note that what is worth noting is that this alpha term is negative. Okay? So, and if you want, and this is the reason why, I mean, because about the spring constants, you can sort of see that these things depend on the spring constants, but they also depend on other parameters, such as the temperature. And that's because we've used a sort of a simple model with sort of binding and unbinding rates.
KBT comes in because it's related to the unbinding.
But yes, exactly. So we've got a two-state model where you've got some hopping rates where the energies are biased by the force. So essentially what happens is I've got an unbinding rate enhanced by the force coming from the spring. So once the spring gets stretched, then it comes off. And this is, of course, what leads to the oscillation. So it moves along, it walks along, the spring gets stretched. Eventually, at some point, that biases the oscillation, it comes off. Then it goes back, goes along, and does the same thing again.
And this model gives you the exact equation.
Yes. Okay, so, okay. And if you want, of course, and you can generalize this, you can make a more complicated model with, with angles and things, but essentially it'll be the same, it'll give you something very similar. Okay, so again, these things are moving in a fluid, so we could again solve our Stokes equation for the fluid. We know what the forces are because but there'll be some hydrodynamic forces. There'll be some hydrodynamic forces. There'll be some velocity field coming from the other bead. So now I've got two of these oscillators. And I'm going to have that the putting in my, I find that the force balance tells me that the velocity will be different from the velocity generated by the other one by the force divided by the friction. So I have this couple, so I have my hydrodynamic interaction, and I could study various cases where I've got hydrodynamic interactions which depend on what substitution. If I'm near a wall or not, I'll get different hydrodynamic interactions. And again, I want to you to recall that the fast variable was amplitude, and the slow variable was the phase. Okay, so we're going to do the same thing we did for the swimmers. I'm going to look in some weak interacting limit, so the separation is quite far. The separation is large, and I can compare the ratio of the hydrodynamic forces to the other forces, so they're weak. So I can write out for each particle. I can write it out in this way. So I've got an amplitude and a phase. I average out over the fast oscillations, and I get some effective slow equation for the amplitudes, AK, and then these I can write as a real part and a phase term, and then you can get an equation for the dynamics of the phase, and it has this form. And there's some function which depends on cos phi, but all you need to remember is that this function is going to be either positive or negative, and the sign of alpha enters into the form of the function, and if alpha is positive, then these the phases will lock to 0. If it's negative, they'll be antiphase, pi out of phase with each other. And actually, if you set alpha to 0, then you have to go to high order in sort of expansion, and you find that actually the dynamics is much slower. But you can still get either in-phase or antiphase synchronization, just much weaker. Okay? So we could then do the same thing again that we did for the particles, but now our variables are not the director, but the phase. and the position of the particles. Okay? So I have a continuous symmetry which can be broken, which is a phase. And so I can write down my nonlinear current in the same way. This term is the driving that's coming from a single oscillator. This term is the hydrodynamic interaction, which is coming from which we have discussed in the last. And so we can then do the same thing and calculate an effective equation for the moments. We can do it again at moments. We can now think about various moments. We can have a density, and we can have a phase coherence term. We do our usual coarse graining. And then, so for alpha is positive, you can get again, because, for obvious reasons, because they want to be in phase, you can get a globally in phase system. But it's negative, then you get something which is locally antiphase, but you have some long wavelength phase modulation. So we also solve this numerically. So we solve them numerically for a line of 100 oscillators.
So you're considering a one-dimensional chain of cilia?
Yeah.
But the hydrodynamic interactions you're using are
The full,
three-dimensional?
we're using the full,
So it's a one-dimensional chain sitting on a surface
Yeah.
with a bulk fluid
above it, yeah. And we also did it for a case where there were just one-dimensional set of oscillators, which was in the bulk. So you could imagine also having a set of oscillators which were far from a wall. You could also do that as well.
Right.
So it's
like that.
yeah, cilia aren't like that, of course.
It has
But
to be-
yes, yeah. But I'm saying that you just get different hydrodynamic interactions. Yeah, okay. And again, we have the same thing. We have some diffusive term which wants to destabilize things, and then you have this sort of thing which causes coherence, and you have some high-order terms which you can get by either going to high order or in your expansion or just putting them in by hand. So if you want the thing that's interesting here is that we have exactly the analogy we had of driven systems and driven active systems, but now we're talking about phase, a phase variable, and how this phase variable can. And so, in fact, we could do exactly the same sort of analysis of the hydrodynamic modes as we did, but now with a different symmetry, with a U1 symmetry, rather than O2 symmetry. So now we can do some little games. So just to finish off, I just want to talk about, we could now make swimmers with an internal phase variable. So I now have a swimmer, and I have an internal phase variable. You could do a realization of it. We take one realization. We took a model by Najafi and Golestanian, and we made one of the arms be the oscillator that I talked about there, and the other arm is just doing the normal thing that model does. And of course, you can show that, in fact, so that is an object which swims and which has a phase variable which is governed by the arm which has this dynamics. And so we can do so this is very similar to the Kuramoto argument for synchronization of oscillators. So this may look familiar to some of you. So we can define the polarization as we had before. We have our phase variable, and then but there's also a phase coherence, phase polarization variable. And of course, we're going to get again some set of equations for these which are coupled. I don't want to bore with you, but you can generate them, derive them. And you can let's just look at some simple systems. I could now imagine that I have my polarization and my phase. You get, again, as I said, you get some coupling term. You can essentially eliminate that pi field, and that's what gives you these nonlinear terms in here. But all you need to remember is that these terms here are proportional to the force. These are the terms that give us these are the hydrodynamic terms that give us the force dipole. And this term was the synchronization term, which came from the internal modes. And so you can get essentially a whole zoo of behaviors. So you can have a system which where, for example, it's not polar, then by switching without synchronization, it would be not polar. You switch on the synchronization, And you go from a case to the case where it's polar, or you could have the other way around. You have them not polar expressions, and it all depends on the signs of the alpha term, which is the term which determines whether it's equal or not, and the sign of the forced dipole. So by playing with the forced dipole, that you can get essentially the zoo of behavior.
So physically, how did the internal U1 variable couple to the polarization? Where did that come from in the physics of the model?
So I mean, you can think of it this way. So I can think of, let's say I have two swimmers or objects. So this one has phi 1, phi 2, and then I've got, let's say, I've got another set, but with a different phase. So okay, phi 1, phi 2 prime. So now because the phase, okay, so the way we get the phase variable is I mean, you can say for one model, just a single model, I can take one arm. I have one arm, this arm here has, so F over gamma. So this is doing my dynamics, and I have my F is equals to whatever it is.
That's you're treating that as an actual position.
Yes.
It actually moves and generates flows.
Yes.
Okay, so it's not an internal variable in the sense that it really corresponds to some physical motion.
Yes. Okay. Yeah. So I'm saying that, but I'm saying that actually, I would say that you could always construct an explicit model for which that's true. But this is just saying I have an object which undergoes some internal dynamics of a cycle, and
that dynamics influences the outside world.
Yes.
In some way, that
yes, and the point is that is not so. In some sense, it's sort of saying instead of having an object which where you prescribe the motion, I have an object where I prescribe motion is fixed for all time. The motion depends on its environment. So I have an equation of motion which is given by x by this, and then I see what happens. Oh, sorry, 2 minutes. Okay, so maybe I can just finish. So what have we done today? So well, I guess we've studied look at hydrodynamic interactions, how promoting order at mean field level. We looked at these swimmers in 2 dimensions. And we saw that we could define these actively driven liquid crystal transitions. And we saw the usual instabilities to these complex patterns, but weaker than the 3-dimensional case. And if you want, using similar techniques, we can show that you can get synchronization of oscillators by hydrodynamic interactions. And I mean, it's sort of obvious that you can now say that now, once you have this framework, you can now basically do all the games that you did with active particles, but for phase oscillators. And once you have an explicit model for the forces, so I can essentially write down I can do hydrodynamic theory, and we see analogs. I mean, so if you want this perspectives, so you can see analogs of the splay and the bend instability. But here, these are of the phase variable. So I start off with a homogeneously old thing, and I see variations in the phase, which because the phase couples to the there's a force in the fluid which is coupled to the phase, so I can get. So you get, if you want, if you want, there's a hope for a sort of hydrodynamic theory of synchronization, and you can easily see that you can generalize to higher dimensions. So once you have the framework, you can do it. So I think this is quite a promising way to look in a very general way at synchronization problems. So thanks.
The final equations you got for P and M.
Mm-hmm. Yeah.
It wasn't obvious where the long-range nature of hydrodynamics fed into it, because those are also equations whose general form you might have guessed at on symmetry grounds. So
basically, the way the hydrodynamic interactions enters is this will be some integral over.
Right. So the fact that there's a bulk long-range hydrodynamic interaction doesn't enter in a serious way into these final equations.
Yeah.
Because
So,
this is-
in fact, what interesting thing about this is that you can now imagine having an oscillator where you have physical things causing synchronization. So those would correspond to essentially you want different values for those coupling constants. So of course
I
that's
think what Trum's getting at is that there are no divergences coming from the long-range thing.
Yeah, there's
High frequency interaction is effectively short-range.
range. Yes.
Because the intervals you have to do to get these guys are all
all
fine.
Right,
converge.
yeah.
Yeah, that's what I was trying to say. Yeah.
Yeah.
I think we should break for lunch. So let's thank Kevin again.